Hello everyone, welcome to the lecture series on kinematic analysis of mechanisms using analytical methods. Under this we are studying analytical methods for velocity and acceleration analysis of slider crank mechanism, complex algebra and vector algebra methods for kinematic analysis of planar mechanisms and analysis of Hooke's joint. In today's lecture, we will discuss on complex algebra and vector algebra method for kinematic analysis of planar mechanisms. Hello everyone. In this video we will see how to perform velocity and acceleration analysis of planar mechanisms using complex algebra method. Let us consider a link OP pivoted at point O so that it can rotate about point O. Now when the link rotates about O, its extreme point P will rotate the pivot point O in a circular path. Under such situation, we will determine the velocity and acceleration of point P when it rotates about O using complex algebra method. For that, let us place this link in a complex plane which consists of one real axis and one imaginary axis. Say this is real axis and this is imaginary axis, and we have placed the coordinate system, complex coordinate system, at pivot point O as its origin. Now at the instant shown, let us suppose that the instantaneous displacement of the link from real axis is theta and the link is rotating with angular velocity of omega radian per second in counterclockwise sense. Now the very first step is to define the position of point P relative to O using a position vector. So I will draw a position vector from O to P. So this is my position vector drawn from O to P. This position vector defines position of P relative to O. Let us name this vector as vector R bar. So what is R bar? R bar is the position vector defining position of point P relative to point O. Now in complex form, the vector R bar can be written as R bar equals to R e raised to I theta, where R bar is the position vector of point P relative to O, R is the magnitude of vector, that is length of vector R bar, and e raised to I theta is the unit vector in the direction of vector R bar, in the direction of vector R bar. So in all the problems we will represent any vector using this convention in the complex form. R bar equals to R e raised to I theta, where R bar is the vector or name of the vector, R is the magnitude of vector R bar, and e raised to I theta is the unit vector in the direction of R bar. Now this is the position vector. Now as the link rotates about O, P will travel along a circular path. It will rotate about O with angular velocity of omega radian per second. So it will have some linear tangential velocity v. To find out the velocity v, we have to differentiate this equation with respect to time. So velocity of P relative to O vector form is equals to time derivative of position vector. So this is equals to time derivative of R into e raised to I theta. Now after differentiating this using the product rule of differentiation, we get R constant, derivative of e raised to I theta is e raised to I theta, and derivative of I theta is I theta dot, plus now e raised to I theta is common and derivative of R is R dot. This is equals to r, we will eliminate this imaginary number I. So I into e raised to I theta is equals to e raised to I theta plus pi by 2 into theta dot. Theta dot is the rate of change of angular displacement theta, or time derivative of angular displacement theta, which is nothing but angular velocity of the link omega, plus r dot e raised to I theta. Now what about this r dot? R dot is the derivative of magnitude of vector r bar, or the length of vector r bar. Now length of vector r bar is constant. Since link OP is a rigid link, distance of P relative to O is not changing. Okay, so derivative of r dot or r bar, or the time derivative of the magnitude of vector r bar, that is r dot, is 0 because r is constant. Length of vector is constant, or distance between P and O is constant. So the final equation for velocity vector, so VPO is equals to r omega into e raised to I theta plus pi by 2. This is the velocity of P relative to O, which I have written here. So velocity vector of P relative to O equals to r omega e raised to I theta plus pi by 2. Now in this equation, this is again in the complex form as shown here, where this represents velocity vector of point P. Velocity vector of point P relative to O. R into omega is the magnitude of this velocity. R into omega is the magnitude of this velocity, and e raised to I theta plus pi by 2 is the unit vector in the direction of velocity vector. So unit vector in the direction of v bar, which indicates the direction of velocity of P relative to O. Now from this equation, you can see magnitude is r omega and the direction of vector is e raised to I theta plus pi by 2. That means it is leading the position vector, which is as theta, by pi by 2. So we can represent this vector like this: theta plus pi by 2. So this is velocity vector, theta plus pi by 2. Theta plus pi by 2. This is the direction of linear tangential velocity of P relative to O, as indicated by this equation. Now to find out the acceleration, we will differentiate this equation with respect to time. So acceleration of P relative to O equals to time derivative of velocity vector. Now let us differentiate this equation with respect to time. So acceleration of P relative to O is equals to r omega common, derivative of e raised to I theta plus pi by 2 is e raised to I theta plus pi by 2, and derivative of I theta plus pi by 2 is I theta dot, plus, now this side common, e raised to I theta plus pi by 2 common, r is constant and derivative of omega is omega dot. This becomes equals to r omega theta dot. Now again we will eliminate this I, so e raised to I theta plus pi, plus r omega dot e raised to I theta plus pi by 2. Now finally this becomes theta dot is rate of change of angular displacement of the link, which is equals to angular velocity, which is equals to omega. So r omega square e raised to I theta plus pi, plus time derivative of angular velocity is angular acceleration alpha. So r into alpha e raised to I theta plus pi by 2 is the final equation for acceleration of p relative to O. Now you can see this acceleration vector is composed of two components, r omega square and r alpha. The first component is called as centripetal component of p relative to O, which is equals to r omega square e raised to I theta plus pi, where r omega square is the magnitude of centripetal acceleration. This is the magnitude of centripetal acceleration, r omega square, and e raised to I theta plus pi by 2 is the unit vector in the direction of centripetal component. Unit vector in the direction of centripetal component, or it indicates the direction of centripetal acceleration of p relative to O. The magnitude is r omega square and direction is theta plus pi. So this is theta plus pi. This is centripetal component. Theta plus pi is the centripetal component. Now in this equation, second component r into alpha is called as tangential acceleration of p relative to O, and this is equals to r into alpha e raised to I theta plus pi by 2. Now again in this, r alpha is the magnitude of tangential component and e raised to I theta plus pi by 2 is the unit vector in the direction of tangential component of acceleration of p relative to O. So its direction is theta plus pi by 2. So theta plus pi by 2. Here is the tangential acceleration of p relative to O. This is the direction of this vector. So velocity is r into omega, linear tangential velocity, and acceleration of p relative to O consists of two components, centripetal component and tangential component. Vector sum of both these components will give the total acceleration of p relative to O. Thank you. We have seen the kinematic analysis using complex algebra method. Now we will continue with vector algebra method. Again, let us consider link OP, which is pivoted at point O so that it can rotate about point O. Now when the link rotates about O, P will rotate about O in circular path and it will have some linear tangential velocity V and two components of acceleration, radial and centripetal components of acceleration. Now in the very first step, we will define the position of P relative to O using a position vector, say r bar. Let us suppose that instantaneous displacement of this link with respect to horizontal axis is theta. Now this vector r bar can be represented as r bar equals to r cap, where r cap is the unit vector in the direction of vector r bar. Unit vector indicates the direction of vector r bar. Now this is the position vector. R bar is the position vector. R bar is the position vector. R is the magnitude of the vector and r cap is the unit vector in the direction of vector r bar, which indicates the direction of vector r bar. Now to find out the linear tangential velocity of p relative to O, will differentiate this equation with respect to time. So d by dt r bar will give the velocity of point P. So velocity of point P is equals to time derivative of r cap. This is equals to r common derivative of r cap is r cap dot plus r cap common, derivative of r is r dot. Now we have seen, since the link OP is rigid link, distance of P from O is constant. So length of vector r bar, that is r, is constant. So since r is constant, its time derivative will be 0. So r dot is 0. So for velocity we get r into r cap dot. Now what is it? This r cap dot. R cap dot is the time derivative of unit vector in the direction of vector r bar. That is, it is the derivative of direction of vector r bar. That is, it is the derivative of angular displacement of vector, derivative of theta dot. So r cap dot is angular velocity of p relative to O. So r cap dot is omega, and the vector direction of omega is the direction perpendicular in which perpendicular to the plane in which omega acts, which is indicated by cross product of k cap and r cap, because k cap cross r cap is a vector perpendicular to r cap. So this vector represents the direction of angular velocity omega. So we can write velocity vector of p relative to O is equals to r into omega k cap cross r cap. So this equation gives the velocity vector of point P relative to O. In this, r omega is the magnitude of linear tangential velocity, and k cap cross r cap indicates the direction of this linear tangential velocity, which is perpendicular to the plane in which r bar is acting. Now to find out the acceleration of point P, we'll differentiate this equation with respect to time. So acceleration of P is equals to d by dt r omega k cap cross r cap. So finding out the time derivative, r omega common, derivative of k cap cross r cap is k cap cross r cap dot, and direction of r cap dot is k cap cross r cap, plus r is constant, k cap cross r cap now common, and derivative of omega is alpha. Time derivative of angular velocity is angular acceleration. This is equals to r omega, r cap dot is omega, so r omega square k cap cross r cap plus r alpha k cap cross r cap. Now this is the cross product of two perpendicular vectors, k cap cross r cap, and this product is equals to minus r cap plus r alpha k cap cross r cap. So final equation for total acceleration of p relative to O in the vector form is minus r omega square r cap plus r alpha k cap cross r cap. Now you can see once again the acceleration component has, or the total acceleration has two components. This first component is called as centripetal component of acceleration, and second component is called as tangential component of acceleration. Magnitude of centripetal component of acceleration is r omega square, and its direction is minus r cap. So if this is vector r bar, r cap is the unit vector in the direction of vector r bar. This is my coordinate system. the direction of centripetal component r omega square is minus r cap. This is direction of r cap from O to P. So minus r cap. This is the direction of centripetal component of P minus r cap. And second component is tangential component of acceleration, whose magnitude is r into alpha and direction is k cap cross r cap, which is perpendicular to the plane in which r cap acts. So this is the direction of tangential acceleration of P relative to O, vector perpendicular to the vector r cap. Okay. So this is how we can solve problems on velocity and acceleration analysis of planar mechanisms using complex algebra and vector algebra method. Thank you.